All right, here we're going to start chapter 2, basic atoms, chemistry, water, that sort of thing. So let's start with what is matter. I think most of you get the idea. Things are either matter or space or energy. Um, I'd like to point out here that the three types of matter that we'll primarily be talking about are solids, liquids, and gases. So you might say that, but I would like to add in another one. So I would like to add in uh, essentially something called plasma. All right, so plasma. Let's make that font a little larger here for you. We will increase that to maybe 16. There we go. So plasma. So what is plasma? It sounds like, oh, isn't that part of your blood? No, plasma is when you take atoms, and as you know, the atoms are formed from electrons, protons, and neutrons. But the electrons, protons, and neutrons are structured together. Like in the nucleus, we're going to talk about here in a second, there are neutrons and protons, and flying around the outside are like planets around the sun. There are electrons. Well, when you really add a lot of energy to them, heat mainly, those atoms, those parts of an atom, the electrons, the neutrons, the protons, they fly apart. And so when you heat up something really, really hot, thousands of degrees, like on the surface of the sun, the atoms fly apart, and they're no longer atoms anymore. They're just free neutrons, free electrons, and free protons. And those, when they're that energetic, and they're so energetic they can't form into atoms, then we call that plasma. And plasma, it's kind of like they're free electrons, neutrons, and protons that we're going to actually talk about here. And so energetic. I can write off of the side of that. I didn't realize that. So they're so energetic that they don't form atoms. They just stay free. And we call that plasma. You see it on the surface of the sun. All right, and you see it in the spark of electricity. The spark, when you plug something in, you see that spark. That's actually plasma. That we think of that as electricity. That's not electricity. That spark is plasma, and that is actually what burns you. It's the free electrons, free protons, and free neutrons flying out with so much energy that they hit your skin, and they actually add that energy to the atoms in your molecules and in your atoms, and make them fly apart and damage you. So that energy gets transferred to you, and of course it damages you. And so realize that's what plasma is, and it's actually that spark when you plug something in or something like that. All right, so we move down. Smallest functional units of matter that form all chemical substances, that's an atom. I just mentioned it. Cannot be broken down. This is important here. Let's go back here. Cannot be broken down further into substances by ordinary means. Now up here I said you could turn it into plasma. All right, well, this doesn't count plasma. Plasma is not a substance. Plasma is another form of matter, so you don't count it as a substance. They're talking about atoms here. When you make atoms, you have substances. All right, you have true thing, but it's these smaller pieces, when they're free, are still matter. The electrons, the protons, and the neutrons, but they're not atoms, so not substances. Chemicals are when we start adding atoms together and forming molecules. So we have bonds. The atoms themselves are the elements. All right, you can think of the elements out there. You've seen the chart. Hopefully you've had some chemistry. And the atoms bind together to to form molecules. These are much larger, of course, because they've got all kinds of atoms in them. And you go take chemistry, you're essentially learning how atoms form molecules and then reform. So how do you turn one molecule into another one? You move the atoms around. That's chemistry. All right. Each type of atom has a chemical element, and they're they're the atoms themselves. Different atoms form different are called elements. All right, because they have different number of protons and electrons, and we'll take a look at this in here in just a second. So protons, neutrons, and electrons that I've already been talking about. All right, electrons. Now, the protons themselves are a positive charge, and they're in the nucleus. All right, notice here it has protons, the little red pluses here. The neutrons are kind of neutral. They don't interact with many things because they don't have a charge. They're also in the nucleus. And these are heavy. All right, they're found in the nucleus, and they're heavy. The electrons are much lighter and much more energetic, and they have the negative charge, and they spin around the outside like planets around the sun. So the most basic atom, and one we'll talk about, is the hydrogen atom. And it's the only one without neutrons, at least in nature. You can kind of force the neutrons out sometimes and things will work. But the only one that naturally occurs without neutrons is hydrogen. It has one electron and one proton. This here is a helium, and you'll notice that you always balance, under normal circumstances, the number of protons and the number of electrons. These will almost always be the same if there isn't something strange going around, because that makes the atoms more stable. And the number of neutrons can be altered, but you would normally see the same number of protons and neutrons. So to be happy, you usually have the same number here. The neutrons are less important in them being the same number, but you normally do want the same number of protons and electrons. Otherwise, you have a charged atom. That atom has the wrong number of protons or electrons. Actually, you really can't change the protons. If you change the protons, you've changed it to a new element. The protons determine what element you have. All right. The electrons determine the charge that it has, and we'll talk about that. So, modern model of the atom. You don't have to know. I'm not going to ask you this question about Rutherford. All right. So here we have a picture. If you want to look through it. I'm not going to ask you this either. This is essentially his experiment, so you can skip that one. All right. No, we're good with that. And we're good with all the rest. So you can skip that. Now, electrons occupy orbitals, so they orbit around, like I said, a mini solar system here. You do need to know that. I kind of mentioned that before. And let's see, electrons travel region. I will explain this in a different way. So you might read it, but I'm going to explain this in a different way. But I do like this one here. Better model of an atom is a central nucleus surrounded by a cloud of electrons. Think of that. That electron moves so fast that it's kind of everywhere all at once. That sounds weird, but it's moving near the speed of light. So really that electron, when it's spinning around so fast that it kind of is like everywhere all at once. But it does spin around. All right, now I am not going to ask you about orbitals or electron shells at this point. Just realize there are kind of layers. This one describes it as when you have one electron, it's kind of spinning around, or one or two, it's going to be in here. Then you add more, and the shell gets bigger. That's all this is really saying. That, you add more electrons, well, the area in which you might run into it is going to change, because I've got more electrons, so they kind of have an orbit that's further away from the nucleus. You could think of it that way when I add extra electrons. And they get some weird shapes. To tell you the truth, I've been reading on this, and this is probably not quite the way it works, they think now. So I don't feel too bad about not teaching it to you, because they're going to have to change the textbooks soon, because this isn't correct. Um, so this would be good to know, though. If you have nitrogen, it means you have 7 protons, and if this atom is going to have no charge, it's going to need 7 electrons. If I change the number of electrons, it's going to change its charge, either positive or negative. Since electrons are negative, if I add one, it's negative. If I take one away, it becomes positive. That would be a good question. So remember that. Remember how you become positive and negative in an atom. You look first to see how many protons there are, and if you have that exact same number of electrons, it's 0. There's no charge. But if I add one, if I add an electron, and that's all you can do here, you either add an electron or take one away. If I add an electron, since it's a negative particle, your charge is negative. If I take one away, well, now there are fewer of these than these. These are positive, so now you have a positive charge. So if you have 6 electrons, you have a +1 positive charge. All right, let's see here. This is kind of showing you where the electrons show up. This is not a chemistry class, so I'm not interested in you learning about orbitals as much as I am you just knowing the general idea behind positive and negative charges more than anything else. So keep that in mind. Understand what I just said here. This is actually important. When you have something that has a positive or negative charge, it is often called something. So I might use the term ion, I-O-N, and that means it's a charged atom. So an ion. Might keep that in mind. Let's see, we're going to skip this. Protons. Now this is also important. What element do you have? It's based on the number of protons. So that gives you your atomic number. Your atomic number is just the number of protons. And so hydrogen has an atomic number of 1. If you have 1 proton in your atom, you are hydrogen. If you have 2, you are helium, etc. That is in the general periodic table that you see on the walls in your chemistry class. Here we go. I'm predicting what they're talking about from each slide to the next. So we're not going to use the periodic table. If we did, it would just be to find the number of protons in that particular element, that particular atom type. In other words, that element, helium, you'd go look it up and you'd say, oh, there are 2 protons there. I should also have 2 electrons. If I have 3 electrons, I have a negatively charged helium. Here are the basic ones, the ones that are used mostly in biology. So they don't give you the full chart. Notice 1, it means 1 electron, 2 means 2 protons, sorry. 1 means 1 proton, helium has 2 protons, etc. So here silicon has 14 protons, all right, just to give you an idea. We won't be using atomic mass in this class, so we can skip that. All right. Now here we're talking about charges. All right. Mass versus weight. This is an important thing to recognize. This would make a nice little question, multiple choice or something, or a true-false. Weight is determined by gravity. In other words, it's the attraction of 2 objects. If you're in space, you have no weight because there's really nothing pulling on you. You got to get close to something for it to pull on you. We're close to the Earth, and it's big, so it pulls on us really hard. But you weigh much less on the moon, and this is all weight. So your weight changes depending on how close you are to something big. So you can have 0 weight, all right, when you're close to big. Now, the idea of mass is something different. Your mass is going to be the same wherever you're at. It's kind of about how much stuff there is of you. So realize there's a difference between weight and mass. Mass is how much of you there is, and weight has to do with how close you are to something big. All right. We won't be talking about moles in here. It's very important for all science to understand moles. Um, but I will leave that to chemistry to teach you that. We won't use moles in here. Isotopes are when you get weird numbers of neutrons. So normally I said before that if you have 6 protons, you usually have 6 neutrons. These don't affect the charge, but they do affect the mass. And so those are called isotopes when you get the, maybe I put 8 neutrons in there with 6, 8, there we go, 8 neutrons in there with 6 protons. That's what they're doing here. That changes its mass, and so they actually call it the atomic weight, but it should be mass probably. And that would indicate that this is going to have some different properties than normal carbon. This is carbon 12, which would have 6 and 6, but now it's carbon 14. Of course, it has a different mass now, or on Earth, it's going to have a different weight as well. Usually when you get the wrong number of neutrons, it's radioactive, and so they call them radioisotopes. So when you got the wrong number of neutrons, it's an isotope, and if it's radioactive, it's a radioisotope. So those are radioactive materials and can be dangerous. All right, so keep that in mind. This would make a good little question as well. How do you get radioactive elements? You usually, it's not the only way to get them, but you usually change the number of neutrons in your nucleus, and so that it's off from the standard number. We'll pretend that it's always the same as protons here. But so normally you would think you have 6 because you have 6 protons. That's how many it makes to take carbon. You change the number of neutrons and you've got something radioactive. All right, we'll skip this. Now, these are some of the more important elements for life: hydrogen, oxygen, carbon, and nitrogen. And water is very important. And of course, what do you make water out of? You make it out of oxygen and hydrogen. And all living things require carbon, DNA, etc., etc. And nitrogen is also needed for DNA and proteins. So these are the 4 big ones. There are a couple of others, but these 4 are definitely number 1 as far as how you make, what atoms you need, what elements you need to form living matter. All right. You can... The main idea is oxygen and hydrogen here make water. Proteins and DNA and things like that are going to use nitrogen and carbon as well. All right. You can skip this. Chemical bonds. Now these atoms come together and form bonds, and they kind of like are electrically, they get charged, and often they will attract one another. There are other ways for them to attract, but some things naturally bond together. And in this particular case, we'll just call chemical bonds whenever 2 atoms bond together, we form a molecule. And that's what this is: 6 carbons, 12 hydrogens, and 6 oxygens. And that is, let's see, what is that? Methane. I'm trying to remember. Methane is 1 carbon. Hexane. Oh, of course. Yeah, hexane. Let's see. Water. Let's see. Hexane. What else do we? No, that's not hexane. It's got the oxygen in it. Oh, is that a sugar or an alcohol? You don't know. You don't know how the oxygens and the hydrogens are bonded together. So I can't tell you there. I can tell you H2O is water. I'm not a chemist myself. Covalent bonds are the ones that we will talk about the most. All right. And then hydrogen bonds are important for water. and sometimes when we talk about proteins. So this one is secondary. How you form the strong bonds between uh, that form molecules that we're going to talk about, like the ones that are strong and don't break, those are covalent bonds. So keep in mind that covalent bonds are strong. A true-false question might be, which is stronger, or covalent bonds are stronger than hydrogen bonds? True. All right, covalent bonds are stronger. Hydrogen bonds are weak. This is electrostatic type bonds. They're very weak. You can pull them apart by hand. Weak. Let's see if I can write in here. I could put text, but I just going to draw it there. All right, so strong bonds, covalent, weak bonds. So if I want to break a covalent bond, I'm going to have to, in other words, make the atoms break apart, make the molecules break apart into individual atoms. I'm going to usually have to do add some major energy to it. I would say boiling would be a good way to break covalent bonds. When you cook food, you're basically breaking the bonds in the molecules in the food down so that they're easier to digest. All right, that's the idea. Hydrogen bonds, really simple. What holds water together is a hydrogen bond. And so water you can separate, well, it does it on its own by gravity. You just, water spills out and it separates. It's actually one of the things that makes it a liquid. The bonds are so weak. But hydrogen bond, maybe something like two pieces of paper that stick together, stuff like that. They're electrostatic usually in nature. Electronegative is the technical term. Water sticks together using hydrogen bonds. Covalent bonds, however, are much stronger, so a lot more energy. You got to boil something to make it fall apart. Here, it barely holds itself together with a hydrogen bond, so very weak. Ionic bonds we won't be talking about. They're in metals, and living things don't use ionic bonds very much, so we don't talk about them much. These are the two that are used in living things, because to break these bonds, it's got thousands of degrees, way more than boiling. All right, boiling, covalent. Here, hard to even keep them together. And here, it's like you aren't breaking them without adding some major energy. All right. You can have single, double, and triple bonds. They have more energy. In other words, if you have a double bond, it has more energy than a single, but less than a triple. And so a lot of times we store energy in the form of triple bonds. Something you might have heard of is trinitrotoluene, TNT, or dynamite. And the reason it explodes is because there's a lot of energy. There's nitrogen in there, trinitro, 3 nitros and toluene. So essentially they're telling you that you're taking nitrogen and you're creating triple bonds in these molecules, and if something causes those triple bonds to break all at once, they release a lot of energy, and that's why dynamite explodes. TNT, trinitrotoluene. All right, fluorine, just giving you an idea. What happens here and how this works, and hopefully you've seen this before, is that these orbits out here, when you've got this innermost orbit, it likes to have 2 electrons to be full. All right, and this outer orbit would also like to be full. Now this orbit, though, see here, 2, there are 2, it's happy because there are 2 there. This one, 1, 2, 3, 4, 5, 6, 7, it would like to have 8. It'd like to have another atom here, but another electron here to kind of fill this orbit out, this orbital. This one also would like to have 1. So they both like to have 1. And so when 2 of them want 1, they can share. And so they're both happy. This one kind of pretends that they have 2, and this one pretends that they have 8. And so they're sharing these to make both atoms. They're not perfectly happy. They'd rather be happy in the sense that they had 1 of their own. But if we share it, it's good enough. And this sharing is what causes chemistry. All right, the chemistry that we think of when you take a chemistry course, it's all about these covalent bonds and these atoms sharing. So they get close to each other and they start sharing electrons together. They form what we call a covalent bond. This is a covalent bond. And to break this, you would boil it. Okay, that's about the right amount of energy usually to break some fairly serious covalent bonds. And basically these two atoms would break apart, breaking that bond. And so as long as they're happier being shared, so there's conservation of energy here to share the bond, so it happens automatically. In other words, there's nothing forcing it. It's that when they come near one another, they're going to share this electron because it's energy. It conserves energy. There's less. They're more stable. That's a better way to say it. If they're sharing than if they're not. So therefore, this is like a spontaneous thing that will occur, and that's essentially what we call chemistry. All right, so let's move on. Octet. That's saying that this outer shell likes 8. This inner shell likes 2. So you can see here, this one only needs 2 to be happy. This outer one needs 8 to be completely happy. So if you can somehow get them to share, maybe you have an atom that wants 3. Well, if this one also would like to have 3, then they can share, and they can share amongst themselves. That'd be a triple bond. All right. Let's see here. Carbon, nitrogen, showing you the orbitals here for the main ones. These are the ones that you will see the most in living things. And so learning to make bonds. So let's think about this. Oxygen has 1, 2, 3, 4, 5. Oh, 6. Okay, right in the outer shell. So the outer shell is 1 here, 2, 3, 4, 5, 6. But that octet rule that we just saw up there says it wants 8. So it would like 2 more. So it wants 2. Wants 2. Would like to have 2 to share with someone. It would like to share with someone. Now here, hydrogen has 1, but it's only got this inner shell that only holds 2. So it would like 1. So this one might come near an oxygen, this hydrogen, and it would go, hey, I want to share with you. And they'll go, okay. But both of them are, actually the hydrogen would be happy with that. It's sharing 1. But the oxygen is still kind of unhappy. So another hydrogen could come in here and share with it to make the oxygen happy. This hydrogen is now happy to be sharing, say, this electron here, and this one being shared over to there. Think of it that way. But another one could come in here, another hydrogen, and it could share its electron, all right, and this one would share back with this one. This would be another hydrogen identical to this one. And now the oxygen would be happy. Both of its electrons get shared, one with each hydrogen, and what that would do is form 2 covalent bonds, a covalent bond between the oxygen and this hydrogen, and another covalent bond between this oxygen and this hydrogen. So with that going on, you now have H2O. All right, 1 oxygen, 2 hydrogens, and they're covalently bonded together, and they're happy because they're sharing their electrons. This one has a kind of pretend 8, and these two have like pretend 2. They're really not theirs completely. They're sharing them, but it's better than not having them at all, being on their own. And so therefore those bonds are created, and we have water. So water forms, if you put hydrogen and oxygen together, water will form, given the right temperature. All right, so here they're just showing 2 oxygens sharing their electrons. We'll skip this for now. All right, and you can move on to hydrogen bonds. Now, hydrogen bonds are much weaker They just have to do with whether or not you have a charge, or you're happy or you're not happy kind of thing. You got the right number, or you got the wrong number. Um, I'm going to do a different video on water, and I'm going to do it just for me, my special video on water. And so you can read this, but I'm going to do my own version of water. So you'll need to watch that video. And we're not going to do ionic bonds, they aren't used that much. You can go take that in chemistry. All right, let's see. Now, free radicals, I'd kind of like you to know this. These are charged particles. So it's, if you remember, it's when they lose an electron, and they'd rather be some, you've got a certain number of protons in your atoms, and so the number of electrons should equal the number of protons, even in a molecule. All right, we talked about it in atoms, we called it an ion. But here, we've got this idea that we have them, they're bonded, but then once they're bonded, they still get an extra electron, and maybe an extra one gets thrown in there. They're happy, and then someone throws in an extra electron, and that's an ion. And here that's what you'd say, call it in chemistry. Here we're going to call it a free radical, and a free radical has a tendency to damage your cells. It messes up the chemistry. You can think of it that way. And the way to get rid of free radicals are to eat foods that are antioxidants. Vitamin C is an antioxidant, so fruit tends to be have antioxidant properties. Blueberries are supposed to be really good for that. Don't know if that's really true or not, but that's what people say. But the idea is you can eat antioxidants, and your body can produce special antioxidants that will go around and what they call scavenge. Scavenge, yeah. Free radical scavengers are what they're called, and they're little molecules your body makes inside your cells to go clean up and destroy these ions that are going around damaging the inside of your cells. All right. Properties, reactants. The only reason we need to know this is how it relates to water. So the idea is water is really special, and I'm going to do a whole nother video just on water. So I'm going to go through here and go through the slides, and you can read them, but I'm going to do my own video on what makes water special. Read these. I can ask you questions on what's here, so go read the slides or read the book. I will leave that open. I can ask you, but I'm going to do my own videos that are specific on water. You do need to know these terms, hydrophobic and hydrophilic. All right. You need to know why water is special. Specifically know what these three terms are. We're going to use those terms later when we talk about membranes. We need to know what polar is, and I will add that to my video that I will have you watch. We'll talk a lot about that, but you should probably, if you're just memorizing, I hate memorizing, but you probably should kind of memorize this and then watch my videos so that you'll understand why these terms are important, especially with regard to cells and water. Don't worry about molarity. You'll learn that in chemistry, I'm sure. You don't have to worry about the heat of vapor, only in the sense that when I tell you it's good and bad later on, but you don't have to worry about it here. And the states of water. There are actually many states of water, not just liquid, solid, and gas. They've just figured out that there are probably about 10 different states of water. It's kind of interesting. Water is a pretty amazing molecule. And without water, there would be no life. That's the main idea of why we learn about water, is because water is necessary for life. If you go to Mars, what do they look for? They look for carbon, because carbon is necessary to make all the parts of life, and look for water, because chemical reactions can't occur, that the reactions needed for life go on can't occur unless there's water present. But water is a solvent. Things dissolve in it. All right, we won't talk about it much. And here we're done with these slides. I'm going to make a special video on water that's going to be separate from the slides. You should know what the terms I circled here are. You should more or less memorize those, I guess. But I'm going to do a special video having to do with these, because this is there's some very specific things that I want you to know that's much more biological. All right, this is the end of the first video. This is chapter 2. First video for exam 2.